This is a Farm Doc Daily webinar. I'm University of Illinois Extension's Todd Gleason. Welcome. Thank you for being with us. Farm Robotics today, revolutionizing agricultural practices. Naveen Uppalapati is here. Hi, Naveen. Thank you for being with us. This should be a really interesting webinar. Great stuff that you and the other folks are doing here on campus at the University of Illinois with robots in the field. I've seen them a couple of times, and there's some videos that you'll show a bit later that are pretty stunning on what these robots can do now. And I'm looking forward to what they might be able to do in the future. Welcome, and thank you so much for being here.
Yeah, thanks, Todd, for having me here. Hi, everyone. I am Naveen. I'm a research scientist in Center for Digital Agriculture. As Todd mentioned, I'm going to talk about how robotics can revolutionize agricultural practices. And this work is in collaboration with Girish Chaudhary, Girish Krishnan, and a lot of PhD students over the last few years. And also in close collaboration with EarthSense, who is our industry partner. So this figure highlights how there is a trade-off of environmental costs for meeting our needs for the food demands. So here you see that we have a lot of greenhouse gas emissions and water pollution and unsustainable water withdrawals and biodiversity loss with our current agricultural practices that we are implementing. And if we are trying to meet the demands for 2050, which is in this circle, our environmental costs are going to be very huge. So how can we balance this trade-off where we meet our food needs and also take care of environment properly? For that, we need sustainable agricultural practices or regenerative agricultural practices where we take care of the environment also properly as we are producing more food. So currently, most of the agricultural practices are monocultures. What I mean by monoculture is we have single crop species growing in huge, vast amount of land, and we have very well-developed ecosystem of huge equipment where we just need one or two people operating these huge equipment, starting from preparation of the soil to planting, management practices throughout the season, and also harvesting. Next slide, please. And in Midwest, mostly we have corn and soybean rotations going on for several years, and I know farmers who have 10,000 acres with just 2 or 3 people managing the entire farms. So the problem with these monocultures is we use this huge equipment, which leads to soil compaction, and also we give a lot of inputs like herbicides, pesticides, and other things. In addition, there is a lot of soil erosion because we keep for half of the winter, we have our entire farm without any covering, and we lose our topsoil. So which leads to soil erosion, and also we have a lot of nutrient loss. There is a lot of nitrogen being leached into the soil, into the water. So the soils are really under stress, and that is one of the main reason why there is a lot of environmental trade-offs with our current agricultural practices. So how can we grow food in a much sustainable way so that we can transform the entire earth? So we can have these regenerative practices integrated into the farmers' agricultural practices, simultaneously meeting our needs for food and also taking care of our environment. So we believe that robotics and AI together can actually solve some of these problems. So here we have a fleet of under canopy robots where these robots can go under the canopy and they can do several management practices. Like, they can actually do phenotyping, they can collect data on your stem width, corn ear height, and the plant health using the cameras on board. In addition, they can also do cover cropping And these robots can also do mechanical weeding in some spots where the weeds are growing. And they can also do side dressing to the portion of the field where the plant's growth is not as expected. So this entire system, is connected to the network, and the decisions are made by a central hub, on what actions or what data the robots needs to collect. So the few advantages of these robots are scale neutral. Anybody from any farmer having farm size from 1 acre to 1,000 acres can still use these robots. So we can have one, two, maybe thousands of these robots working together on larger fields. We're still not saying that we're going to remove the planting and harvesting things. These robots cannot do those tasks, but they can do these management tasks where we can reduce the number of inputs which we're putting into the ground, onto the plants, and into the environment. And also, these robots also reduce the soil compaction because these are pretty lightweight compared to our heavy equipment which we're currently using in the farms. So here I'm just going to showcase what is our vision for path to this sustainable agriculture. So we want to have better seeds. So you can get better seeds by better phenotyping of collecting the data from your different seeds varieties and seeing which seed variety is going to give you higher yield. And then we also want to see how we can reduce chemicals onto the farms. And then we have next, yeah. And we can also do this integrative agricultural practices. And then we can have these sustainable productive ecosystems. And I'm going to showcase in my next set of slides how the robots are contributing to each step of this inverted pyramid. So although the idea of using robotics in agriculture is pretty cool and gets a lot of traction, but there are several challenges which needs to be solved to actually effectively have these robots working in our fields for 24 hours by 7 and able to address our environmental trade-offs which we are facing with our current agricultural practices. So the first one is, of course, our fields are huge, especially in Midwest. And then compared to, there's a lot of thing going that, we have these autonomous cars going on, and why there is not much movement in having autonomous robots in our fields. One of the thing is, we have very poor data sets availability in agricultural settings. And in addition, every field and every farm is completely different. We encounter and newer challenges, and that's good because the robot is learning newer environments over time, and it's able to learn by itself. So unstructured environment is something which we have to deal with, having autonomous robots solve some of the agricultural challenges. So our first one is a phenotyping robot. This is from a spin-off from a university, EarthSense company, started in 2017. So this robot has 3 cameras on side and 1 depth camera on top. And these cameras on side can actually look at the different features of the plant. And for example, currently one of the major challenges of phenotyping is data collection. There are different plots the breeders have, and the data is manually collected. The data of plant height, the stem width, and corn ear size, and the yield and other things. And it is very intensive process of collecting this data from each of these plots, and it also leads to exhaustion for collecting a lot of data over a same period of time. So these robots, with their advanced sensors, which are simple RGB cameras, um, collect these data autonomously. So you have this high throughput phenotyping. So here you see these robots. So this robot can autonomously navigate through corn and soybean. So this has 2 lidars, one on top and one on back. And using these 2D lidars, it figures out whether it is going in between the rows of corn. And these are the data collected from side cameras, and it is estimating using AI the stem width, and also it is counting the number of corn ears in that particular plot. It also can predict the size of the corn, and here is also counting the number of emergence of the plants. So in this way, you can use this robots for high throughput phenotyping, increasing the speed of better seeds and increasing the yield. So this is the dashboard developed by EarthSense company, where you can see the information for plant height and different other phenotype traits in the dashboard. So based on this, you can take decisions of what seed you want to grow in. So that's the way how we are developing robots to make better seeds. Next, I'll move to the cover cropping robot. So 95% of US farmland is left there for 8 months of the year. And, basically, as I mentioned earlier, this leads to a lot of nutrient loss and soil erosion. You lose your topsoil. So one of the way which is well known to farmers is, this land could be sequestering carbon using cover crops. But there has been less adoption of cover crops because it involves, more labor, because after harvest, you need to plant these cover crops into the field. So you need extra labor time, and also especially in Midwest, the winter, you may have an early winter, and frost may come in, and whatever investments one does on seeds, everything can go for a loss. And also it doesn't have great emergence if you do post harvest. So using the same you know technology, what we used for the phenotyping robots, the robots which can go under the canopy, so we wanted to use robots to also plant cover crops. So what are the advantages of using robots for cover crops is you can plant your cover crops much earlier in the season. So uh, unlike our existing methods of aerial cover crop seeding or post harvest seeding, the aerial cover crop seeding, you have to seed at a much higher rate because a lot of seeds are on the leaves of the corn, so they don't actually touch the soil and don't emerge. And the post-harvest one, as I mentioned, you have very little window of time for good emergence. So we can have the robots go under the uh, corn rows and start planting cover crops much earlier, from August or September even. So by the time of harvest, you have good emergence. This is the picture of the emergence post harvest, maybe after 1 or 2 weeks. So we have this robot which can carry close to 90 pounds of seeds, and then it can actually distribute these seeds within 4 rows towards the right and 4 rows towards the left. So this is a spinner here, which spins at a much higher speed, and that speed gives it the velocity for it to spread the seed for 4 rows towards the right and 4 rows towards the left. So this can take close to 100 pounds. And some of our initial economic analysis shows that we can plant the cover crops at close to almost $5 per acre compared to existing costs of $15 per acre. So here is a video of the cover crop robot going autonomously under the canopy, and it also uses the cameras to navigate. Um, and you see here, maybe next one. So it's actually, yeah, here. So you can see that there is a spinner and the seeds is coming from the bin there, and it is being distributed to the rows adjacent to the row which it is traveling. So we clearly showcase that we have much better emergence than post-harvest and aerial seeding using these cover crop robots. And currently, our existing technology, we can have 5 of these robots with just two operators standing at one end of the field, and these robots can navigate autonomously throughout the row. These robots also have the ability of crash recovery. In this particular video, you can see that this is a 5x speed where we are showing that these robots without any intervention can travel a maximum of 3.8 kilometers. So here you see that this particular robot actually crashed into the corn, standing corn there. So it autonomously recovers. It reverses back, corrects itself, and continues seeding. So this navigation policies, just using simple RGB cameras, have enabled us to scale this up of able to cover crop using robots much earlier in the season. So these are some of the few robots which can assist in our existing monocultures. But as I mentioned, the monocultures are resource and input hungry, and just automating the existing equipment is not enough to realize our vision for sustainable agricultural practices. So the other option is to have these complex annual rotations, which improve sustainability, which most of the farmers currently adopt this of having 2 years of corn and then soybean and rotate these crops. And the other um, alternate solution is having perennial polycultures. The polycultures is growing different species of crops on the same farm on the same land. So how this helps is there is much less weed intensity and pest intensity, and there is less nutrient loss because research has shown that the nutrients which one particular species doesn't take assess the other uh, crop to grow well, and this is a very sustainable system. But we have moved away from this perennial polycultures because there's a lot of manual labor involved, and our existing equipment doesn't fit well with this kind of system. Okay, so we have this plot of scale versus dexterity. So the manual labor is, it has very high dexterity, but it is small scale. You cannot scale it to large pieces of land. And then we have this current agricultural robots, which I showed you earlier in the slides, which are small scale, but they don't have dexterity. They don't have any arms or hands onto them, like how humans have to do some dexterous operations in a perennial polyculture setting. And then we have our existing, low dexterous and large scale equipment, which everybody of us sees almost every day. And then we have this high dexterous and large scale. So how can we have robots which are very highly dexterous, something like, which can actually pick berries from your farm and can also do, pest removal, and also can do pruning and harvesting and other stuff, and how we can make them low cost and intelligent. So I'm just going to talk about this is much in a research level, not in a already implemented in a large scale. Uh, so the idea is, everybody can have their own farm. So we can have the farm on terrace farming or maybe urban farming, even backyard farming. A lot of hesitancies for the new gardeners or growers is the resistance in maintaining it. Everybody likes harvesting and planting, but there are a lot of Japanese beetle affecting those, or a lot of weeds growing. So these are some of the dirty tasks which one need to do to have our own farm. So we want to develop robots which will be able to enable these. So here we show you a berry harvesting robot. So it just uses two cameras, and we have an 6 degree of freedom robotic arm on a similar robot, as I showed you, which is navigating under the canopy. This is a very compact arm, so it has a gripper at the end. So it uses these cameras and some detection, computer vision based detection and motion planning to actually approach the berry and harvest them. So in this video, you see that there are two cameras, one at the base, and which is the pan and tilt camera. So you can see that the pan and tilt camera tries to detect where the berries are. So it is scanning with a depth camera. And once it detects a berry using the depth camera, it gives this particular positions to the robotic arm. And the robotic arm moves to that particular berry, and then it has a camera in the gripper. So it helps it to correct its final errors, and it reaches it, and then this pneumatic gripper closes, successfully grips and plugs it. So we did several tests, and I think this is the 997.5% is in lab testing, and we have 85% testing in real field too. So here we show you a sample video how it is able to pick a cluster of berries. Currently, it takes 10 seconds for picking each berry, which is much slower compared to a human picker. But the advantage of these robots is they can work 24/7. So this, most of the harvest in California, close to 40%, is wasted because there are no workers to harvest them in right window of time. So these robots can actually support these human workers, so to reduce the wastage of fruits. So other task which I was mentioning is about pest detection. So here we have a similar robot with a camera, and it navigates autonomously within the rows of the garden, or this is a high tunnel setting, which is a hoop house. And it can detect bugs. So it has a computer vision model which can detect whether there are harmful pests, whether they're affecting the plant, and the particular robot stops there and then it sprays. You can have your own chemical. So the advantage is we are doing very targeted spraying per plant rather than spraying it on the entire field. This reduces the the amount of chemicals which you are inputting to the field. So this is just showing, I think it's a Japanese beetle. The computer vision model is actually detected a Japanese beetle and sprays. So it's showing it's on a tomato plant in a high tunnel, in a hoop house. So the other interesting thing is we can also do urban farming. So we can have these hoop houses or high tunnels, which is just a tarp on a metallic structure. So this extends the season by 2 months. From April, you can start your season, and you can also have till January. You can grow greens because this maintains the temperature much higher even after winter sets in. So you have a long period of time where you can grow your specialty crops. So we use these robots to do cloning, pest detection, precision spraying, and harvesting. And these again use the vision-based perception and vision-guided manipulation and automated navigation. So we just have two different kinds of robots. One, it is a spraying robot, another one is the harvesting robot, which I just showed you. So with this, I would like to conclude that how we are able to address different parts of this inverted pyramid, like how we have these phenotyping robots which can assist in high throughput data, which helps in better seeds. And then you have cover crop robots, which also reduce a lot of weed intensity, fewer chemicals. And the same robots can be also used for side dressing. You can just have nitrogen side dressed in a particular portion of the field where you have seen that the growth is not as desired. And it can also be used for spot spraying. And then I showed you how we can come to this integrative agriculture of having polyculture systems where you can have these berry harvesting robots, and the same robots can be used for other gardening applications. But we have targeted the berry harvesting is because that's where the business is. And then we can move towards more productive ecosystems. We can have urban farming with robots. This reduces food miles. We don't need to get our strawberries and blueberries and other things from California. It reduces a lot of food miles, the amount of miles for the food to travel to our plate from the place where it has produced. And this robotics, whatever we are trying to pitch it for agriculture, are scale neutral. Anybody, it also can attract newer, upcoming youth and other people to agriculture. They can start with 1 acre or a few acres, test their technology, and if they're satisfied, we can attract more farmers to agriculture. This is part of the iFarm learning series. iFarm, of course, we focus more on the monocultures and how we can use the cover cropping robots and side dressing robots and weeding robots. You can sign up for updates in this go.illinois.edu iFarm updates. So you will get any updates about the field days and the different other demos from industries on our test bed. Uh, yeah.
Again, so if you'd like to, and Naveen, I'll just repeat some of that. You can always learn more about the iFarm at ifarm.illinois.edu, or if you want to sign up to get yourself updates emailed to you, you can do that as well at go.illinois.edu/iFarm updates. We'd like to thank our sponsors on the next slide: the TIA Center for Farmland Research, CoBank, Compeer Financial, Corteva AgriScience, Farm Credit Illinois, Growmark, the Illinois Corn Growers Association, and the Illinois Soybean Association, and our Farm Doc partners as well. They include the College of Agricultural, Consumer, and Environmental Sciences, the Department of Agricultural and Consumer Economics, along with the University of Illinois Extension, the Gardner Agricultural Policy Program, and FBFM. That's the Farm Business Farm Management Record Keeping information in the state of Illinois. We'd like to thank you for joining us as well. We do have some questions. We'll get to those now. Very quickly, just running through the questions, and if you've got some, you can type them in, but we're running out of time at this point. Naveen, do you think it's possible to outfit, this person asks, the autonomous planter robot with a seed drill or similar apparatus? And of course, they understand that it would have to make many more passes than a broadcast seeder might through the field.
Yes, it can be. These robots look small, but they're very powerful. I didn't have one of the video, but we have a video showcasing the power of these tiny robots. They can actually pull a small scale tractor. So you can have a seeder. Uh, it's not a regular thing, but a small sized one attached to these robots and have it seed. Yeah, it is possible.
So a couple of things combined here related to the future. One of them is about the size of farms that might be able to utilize these and how bigger farms might utilize them because of the capital investment required, and what you expect to see develop in the next 5 to 10 years. They're somewhat related, but maybe different topics for you.
Yes, as I mentioned, we are still not replacing, your seeding or harvesting equipment there. We are mainly focusing on the management practices. How these effective management practices of cover cropping and side dressing and spot spraying, reduces the amount of soil compaction, and also ability to grow cover crops and others, has a lot of benefits to the soil, where we're actually, regenerative agriculture. It's we're developing the soil, getting the nutrients back into the soil. So yes, on a larger scale, we can have a fleet of these robots. That's one of the solution, and we aim to do it as a service. So we have 10 or 20 robots coming to your farm and completing these management practices like cover cropping or side dressing in some particular regions. And coming to the second question, Todd, we currently have a target of scaling up to 20,000 acres of cover crops. We got funding from USDA for Climate Smart Commodities Partnerships one. So our goal is within next 2 years, we scale these technologies to 20,000 acres. So at least these is more or like getting into the farmers. Everybody are interested, but the harvesting robots will need some more time because there are several other challenges which needs to be solved. Which I see at this scale, the smaller kind of harvesting robots, which I presented in this particular talk, will need 5 more years to actually come into market for an effective business.
Naveen, thank you. I appreciate it. Very, very interesting. We appreciate that all of you have been with us as well for the day. We do want to thank Naveen Uppalapati for making the presentation. If you'd like to see it again or send it along to others, you can do that later today and then into the future as well, as it will be archived on the FarmDoc Daily website. You can look under webinars in the archive there, or you can visit youtube.com/at FarmDoc. That's down at the bottom of the page at the moment. That's youtube.com/at FarmDoc. On behalf of Jim Baltz, who's behind the scenes running things this afternoon, I'm University of Illinois Extension's Todd Gleason. You have a good day.
Thank you.